Hi everyone. So let me at the very outset thank the organizers for giving me the opportunity to speak here and also organizing this wonderful conference in this great campus at ICTS. So my talk is based on a recent work that I have done with some of the collaborators who are, some of them are the very participants of this conference like Professor Mohanty or Punhait, but I don't see them now in the audience, so I think they have deserted me during my talk. Okay, so as you can see from the title of the talk, it again speaks about memory, and you have already heard about memory effects talk already. There were 2-3 talks in the last week. What my job will be is to impress upon you that how can using memory effects, you can detect something like DSM physics, which closely aligns with the theme of the conference. Okay. So the main 3 things that needs to be emphasized in the talk is memory effect, then there's this supernova neutrinos and the self-interaction. So the plan will be, first I will talk about memory effects and memory signals, and as it has already been discussed quite a few number of times, I will go through it very briefly. Then I will show how memory signals arise in supernova neutrinos, and finally I will discuss self-interaction of supernova neutrinos and address the final question. Okay, so what is gravitational memory effect? So it is a net relative displacement and in very certain cases net relative velocity given by a gravitational wave pulse. As you can see in this figure, a ring of particles after the passage of the pulse, if it retains its original configuration, we say that it doesn't have any memory. But if the gravitational wave burst is loaded with memory, what you will see is that there is a permanent change. So here the ring initial configuration is a circle, and finally after the wave has passed, the configuration has changed. It has become ellipse. It necessarily not be an ellipse. It can be different depending on the scenario, but it will permanently change. And that is why it is called as the memory effect. Because after the wave has passed by, the wave is not there, but its imprint is remaining in the space-time. Okay, so there is a permanent distortion. So how to understand this? This was memory effect that I talked about here. So how it is related to the signal that is coming about. So if you write down the geodesic deviation equation in the transverse stressless gauge, you can write a relationship between the signal that the gravitational wave is coming with the memory effect, with the separation in geodesics. So in order to have memory effect, you need to have a change in the memory signal at initial and final. Okay, and what is this difference in the memory signal? It is basically the time difference at at early times and at late times. So if there is a change in such scenarios, only we'll find there is a permanent change in the detector, and that is imprinted as the memory. So for slowly moving sources, what you can do is basically you can solve the sourced Einstein field equation, which is given by this box Hij bar. Hij is bar, but Hij bar is nothing but the trace reversed Hij, Hij being the gravitational perturbation. And you can show using Green's function techniques that Hij is proportional to the double derivative of the quadruple moment tensor. So in order to have memory effect, you need to have a change in the double derivative of the quadruple moment tensor. So there should be a change in it. However, the quadruple formula to obtain this gravitational wave strain fails for velocities in the relativistic and the ultra-relativistic regime. So what you do in that case, you solve similar to what we do in electrodynamics, where you solve it through the Liénard-Wiechert formula. And for ultra-relativistic sources, this looks like this. I have given 3 examples. So the last 2 examples is the important ones which will be employed when I compute memory effects in supernova neutrinos. Okay. So what happens in memory signal in supernova neutrinos, now that we know memory effects? Okay, so as already discussed by Professor Ajit, let me go through it very briefly. So in core collapse supernova, what happens is that for mass greater than 8 solar masses, red supergiant stars, there is nuclear fusion, and the gravity is balanced by the radiation pressure being fueled by this nuclear fusion. Now what happens is that as the nuclear fuels burns out, gravity contracts, and there's formation of helium and subsequent formation of this higher and higher ordered elements. And once it reaches iron, as iron has the highest binding energy per nuclei, the radiation pressure cannot sustain, and that is why the core starts collapsing. And this core collapses until when it is balanced by the neutron degeneracy pressure. And it starts collapsing like here, and when there is this, the incompressibility rises after certain density, the core bounces back, and there is a shock wave formation, which is given over here. And the shock wave travels outwards, and it is again reinvigorated, re-energized, thereby blasting away the outer surface, and thereby you get supernova. So the question is, what is the role of the neutrinos over here? So electrons, as I showed that it is basically balanced by the neutron degeneracy pressure. So electrons gets converted to neutrons, emitting a neutrino. So there are enormous amount of neutrinos produced. As the core compactness rises to this value, production of neutrinos also rise. So the shock wave that I showed earlier here first stalls, but as there is neutrinos, this gets re-energized and there is an explosion. And energy of this order is produced, and such neutrino burst can lead to gravitational radiation. Okay, so that gravitational radiation being produced by anisotropic neutrino burst is not something new. It has been known since the 1980s. But the important fact is that what you need to note that there should be an anisotropy involved in this scenario. So what you do is basically you solve the Einstein field equations with neutrinos being as the source. So this is the basic formula for the computing the gravitational wave strain when there is this asymmetric neutrino emission. So what this epsilon term is basically given by the luminosity and the anisotropy. So if you do the computation, if there is no anisotropy, you find that there is no gravitational wave radiation. So there should be an anisotropy, and the scenario is shown over here, where n prime is the direction of the neutrino and this capital N is the direction of the detector, which is taken as in the z-axis. And this is the standard gravitational wave strain. Use the detector time. Okay. So now, as we know how memory signals arise in supernova neutrinos, now we'll include neutrino self-interaction to see what is the effect over here. Okay, so recently in 2023, this paper came about where they talked that when there is a self-interaction in in supernova neutrinos, the neutrino burst signal changes. And what they showed is basically this scenario. So you have these neutrinos coming out of the PNS, which is the proto-neutron star, and as after coming out, it doesn't travel with speed c. It travels with a velocity of speed of sound c by root 3, and after a certain radius, it free streams. So there is a new length scale involved in the problem due to the self-interaction. So this is the scenario. Just outside the proto-neutron star, the neutrino density is very high. So neutrino self-interaction occurs. It basically cannot free stream. So the velocity is this, just after coming out of the proto-neutron star. And after traversing a length RFS, which is the imprint of the microphysics, the speed of the velocity is 1. So what is basically changing? Why this is v equal to 1 by root 3 and this is v is equal to 1? So this is the self-interaction details that they took. So the Lagrangian of the self-interaction is like this, which is mediated by a light scalar like this of 10 mega electron volt. And so what happens is that the optical depth initially is high, and after crossing certain length scale, this RFS, it becomes basically 1. So what we assume here, we assume a simplified setup, we assume that this neutrino density follows like this, power law. And so for various values of beta, you can compute the RFS, which is dependent on the self-interaction strength, the self-interaction strength given by G. Okay, so what will happen to the memory signal? So now what happens, as I showed, there is a diffusion region and there is a free streaming region. So just after coming out of the proto-neutron star, velocity is 1 by root 3, and the time domain strain is basically of a relativistic fluid. As I showed earlier, in the very earlier part of my talk, the time domain strain for a relativistic fluid. And after certain radius, the velocity is 1, which is given by a null fluid. So this is the change that happens, and that is why you see a change in the Hij, or the time domain strain. So now what we have done, we have basically taken two values of RFS, the free streaming radius, one at 100 kilometers and one at very high range. What you see that if the diffusion region is high, the RFS denotes the diffusion region. If the diffusion region is very high, the time domain profile is small earlier, but at RFS, corresponding to this U, the time domain strain gets a transition. And this transition happens abruptly. This is because the velocity is abrupt. If the velocity was continuous, this change would have been continuous. And for the 100-kilometer case, since the diffusion region is low, the transition happens earlier in the time domain profile. So as RFS increases, this length scale of self-interaction or free streaming radius, the transition will happen at a later time. And now so we do the frequency domain plots, and then we talk about the detection prospects. What we show that these are not obtainable from LIGO or Virgo. Even for LISA, the decihertz detectors are better suited to detect this. So you see that for the 10 to the power 5 kilometer scenario, you see that this transition happens around this BBO and decigo range. So you need to have a large RFS to detect this effect. But if we have a continuous change of this value from 1/√3 to 1, then you can somehow see there is a gradual, then there will be a gradual change in this, and from there you can understand that there is an imprint of the self-interaction. So for lower values of RFS, detection is challenging for the current and planned detectors. So I will summarize here. So the current work is, so in all of this, when we do this frequency domain strain and the time domain strain, we have obtained analytical results. So this is a very simplified setup and sort of a proof of principle. It is possible to detect, and from this example that I showed, the gravitational memory signal for neutrino self-interactions. So gravitational burst signals are basically studied through these 3D supernova simulations, and that will give a more realistic picture. And also, you are getting neutrino signal, you are getting gravitational wave signal. This can help us in multi-messenger astronomy. So I'll stop here and take questions.
Questions? Yeah, so can the self-interaction strengths within the standard model lead to some observable effects? In the standard model case, can that strength lead to some observable effects?
Yeah, that is small. So if you have G to be the weak interaction, so if this G is around this 10 to the power minus 5, which is, so if you compute the weak interaction scales, which is 10 to the power minus 11 mega electron volt, that is basically the 100 kilometer RFS, and that is not currently observable. So you need to have higher, the self-interaction should be higher than the weak interaction scale.
Okay. Very nice talk. So this is about why that there will be an abrupt change from 1 over square root of 3 to 1. Is there any reason? I mean,
so that is basically that this. So the idea of this is taken from this paper. What we say is that, what they say is that there will, in this scenario, there is this self-interactions, and there the velocity is like this, and after that it basically changes. So what happens is that the optical depth, there is a parameter called optical depth, that becomes 1.
Okay.
After RFS.
Okay.
From RFS it becomes 1. Yeah.
So the mean free path allows them to propagate after that. That's so again, the magnitude of that memory looks very large to me. I mean, it's.
So you can see it from the characteristic string.
Oh, minus 23. Okay.
No. So we took a higher value of RFS because that is in the detectability range, and it is still not constrained. Yeah. But so what is the main issue is that in realistic scenarios this won't be abrupt. So if
over the sources, I mean, this is in the galactic sources.
So we took 10 kiloparsec.
Okay. We need to talk about this. Okay. Thank you.
Okay, yeah, go on.
Let me ask you the basic question about the memory effect. Suppose you have the free space, you don't have anything, and then when gravitational waves passing through, and do you have a memory effect there?
So that depends on the pulse. If the HIJ at initial and final time is same, you can't have memory, right? As I showed in the geodesic deviation equation, if there is a delta HIJ, that gets imprinted into delta Xi.
And where do you have a delta HI? What is the origin of delta HIJ?
Delta HIJ is the gravitational waves so this HIJ change at initial time and at final time. If that value is same, you can't have a change in the geodesic separation between the two. So I am assuming that the geodesics, that the detectors follow geodesics.
But you're assuming that the initial and final value is different. It means you already have the put by hand is a kind of initial condition, isn't it? Suppose you have exactly, pre-space, you don't have anything, nothing.
Yes, yes.
And the gravitational wave pass through.
Yes.
Then
so
you are saying you don't have any memory effect, right?
So what I am saying is that depends on the gravitational waveform. If the gravitational waveform time domain initially and finally changes.
Okay, monochromatic gravitational wave, for example.
If it initially and finally changes, the time domain strain value, then you will have a memory effect.
Initial and final.
So in general, for binary merger scenarios, memory effect has not been included in the waveforms. What they do is that after the binary merges and there is this oscillatory signal, the quasi-normal mode decays and it settles to 0. That scenario you don't have memory effect, because if your HIJ settles after the quasi-normal mode oscillation, it settles down to 0. Your HIJ is finally 0, initially 0, you don't have memory. But in that scenario, you don't have memory, but you need to include memory effect in the template waveform.
Okay, I will ask later.
Yeah,
thank you.
Okay, then is there any other questions? So if not, let's thank Indranil for this beautiful talk.